This is module 8.2, angle bisector of triangles. So the essential question, how can you use angle bisectors to find the point that is equidistant from all the sides of a triangle? So we've already talked about, you have your triangle here, and it's like an inscribed polygon where it's inside a circle, right? And we've all talked about that. Now, what we're doing for 8.2 is you have your triangle, but now you can draw a circle in it to where the edges of the circle are on the edge of the sides of your triangle. Okay, something like that. All right, so our shortest answer is we bisect any two of the angles of a triangle. So you have your triangle and bisect. Remember, bisect means means two. So we're going to cut into two angles. You just need two angles. So I'm going to take this vertice and this vertice, and I'm going to create a bisector. I'm going to create another bisector right here. And basically where they intersect is the middle of where your circle, your radius or the pointy end of your compass needs to be. And then you just draw your circle around it, and it should hit the fine sides of your triangle if done correctly. So just note this drawing is not to scale, but that's the main idea. Now, the point of intersection of the angle bisectors, again, is equidistant from the sides, so equal distance from the sides. And again, what they're talking about is after you do the whole angle bisectors, you get your intersection right here. Basically, it's going to be the same length from here to the side as it is from here to this side and here to this side. So that's what it means by equidistance from the sides of the triangle. All right, so investigating distance from a point of a line. So first things first, you need some patty paper, all right? Patty paper. So grab some patty paper real quick, okay? And I want you to draw this image right here, that angle, okay? Angle ABC, including the rays. Make sure you label the vertices. Then what I want you to do after you create that image is I want you to fold that paper to where both these rays map onto each other. Okay, so you should get some kind of folding crease, like somewhere around here. Okay, again, your folding crease is going to look something like that. Then what I want you to do is I want you to draw it, draw that folding crease, trace it, okay, after you fold the paper on those two rays, and then you're going to label this point on that crease, that folding crease. Now, your turn number one is basically saying, what do you notice about the measures of angle ABP and CBP? So what do you notice about this angle compared to this angle? All right, and measure with a protractor. So you're also going to need a protractor, all right, to verify what your answer may or may not be, okay? And it's okay to compare it with somebody else next to you as well. All right, applying the angle bisector theorem and its converse. So the angle bisector theorem is basically saying if a point is on a bisector of an angle, then it is equidistant from the sides of the angle. So basically, we're told that the angle here is the same as this angle here. Therefore, this length has to be congruent or same as the other length. So this point right here is actually equidistant from A and B, all right? So basically, since the two angles are the same, all right, then the two sides are the same. So that's what I wrote right here. Okay, that's what I'm indicating. If this angle is the same as this angle, then here we go. Okay, that's an angle bisector. That's what I call it, the angle bisector theorem. Now, the converse basically just says, well, if this guy's the same and as this guy, then this angle is going to definitely be the same as the other angle. All right, so again, it's just script flipped. So this time, if the sides are the same, then the angles are congruent. So it's just flipped. Again, converse, if P then Q, the converse is just saying, well, if Q, then P. All right, that's all it's saying. All right, so let's get to the application aspect of this. Yeah, we get some numbers here, and they're asking us to find the measurement of LM. Now, if you notice real hard right here, they do say that these two angles are congruent, and therefore, by the angle bisector theorem, JM should be congruent to LM. So if JM is 12.8, then so is LM. All right, so again, angle bisector theorem was applied here. Okay, since angle JKM is congruent to the other angle LKM, then JM is going to be equal or congruent to LM. And if JM is 12.8, then LM is also going to be 12.8. All right, so LM has to be 12.8. Now, part B is basically saying, well, ABD is going to be, we have to find AB, the angle measurement for that angle. Now, they do give us ABC being 112 degrees. So this whole angle right here is 112 degrees. Okay, and basically, we have the whole bisect angle theorem again. Or actually, this is the converse, because if you notice, this side length is the same as this side length. So by the converse of angle bisector theorem, okay, we know that this angle right here has to be congruent to the other small angle over here. Therefore, it's got to be half. All right, the angle that they're asking for, ABD, is half of the measurement of 112. Okay, the whole thing. So what's half of 112? You should get 56. Yeah, 56 degrees. Sorry, I did some quick math in my head, and it's late, so there's always that self-doubt that kicks in. All right, so again, this is how we apply the angle bisector theorem with numbers, and then we have the converse kicking in for part B because they did give us the sides first, and then that helped us realize that these two little angles are sharing that 112. All right. All right, so your term number 2, find the measure of QS. Again, QS is right here. And look at the angles and see if this is the angle bisector theorem or the converse. So I'll tell you what, also give me the reason. So is it going to be the inverse, or I'm sorry, the converse, or the actual theorem itself? All right, your turn number 3, find the measures. They care about the angular measure of LJM, and they do give you the measure for KJM. So again, KJM is this guy right here, right? So find LJM for me. And that LJM, again, is the whole angle, all right, for those two angles together. All right, so here's the next part of our subject. We did have to talk about angles first to get into this. Basically, we're getting to construction of inscribed circles. So again, just like in the essential question, we did draw inscribed polygons inside of circles, but now circles are inside of our polygons. So a circle is inscribed in a polygon, okay, that means like inside, and it's tangent to the circle. What that means is eventually there's a certain part of that circle that lays flat with the sides of any of the polygons that are relevant to our situation. Okay, so in the figure, C is the inscribed in the quadrilateral. So basically, C here is inscribed, which means it is equal distance from every side of your polygon. Okay, and we're going to see that with triangles and whatnot. But basically, all these guys are congruent because C has to be dead in the middle of your polygon. So in order to construct the inner circle of a triangle, you need to find the center of the circle. And I want to teach you how to use that with angle bisectors. This is also called the incenter of the triangle. So the center of the circle is also known as the incenter. So just be aware of the duality of words in case you see that in the homework or a test or your CASP, who knows, okay? All right, so constructing an inscribed circle, definitely grab your compass. So you're going to need this. Use a compass and a straight edge to construct the inscribed circle of triangle PQR. Now, you're only going to have this part of the cutout, okay? Um, this one right here, that's the one that you create from this one, okay? So everything in pink on the right, that that's something you're going to do, and I'm going to explain how to do it. So first things first, is what I want you to do is I want you to pick two vertices. In this example, they picked P and R, okay? And you're going to draw basically an arc angle, okay? And what's going to happen is, let me make sure I don't lead you astray here. When you draw the angle, now it can be whatever angle length you want. But basically you're just going to draw that, and you're going to get these intersections right here on the outer edge, okay? What I want you to do after you get that is you're going to put this pointy part of your compass right here, and using the same radius on your compass. So again, do not adjust that little middle part right here. Don't adjust that after you use it. Okay, keep it the same. All right. So once you do that, you're going to do an arc like this, okay? And then after you get that arc, you're going to put your pointy piece on this intersection that you had originally, and then you're going to draw another arc like this, okay? And you're going to get this whole X marks the spot type deal right there. Then what I want you to do is go to your next vertice and draw that big, huge arc that you did the first time for vertice P, okay, for that corner, for that angle. And then what I want you to do is you're going to notice these two intersections here at the outer edge of your polygon, your triangle, okay? And same as before, you're going to put the pointy end here, and you're going to draw the arc, okay, right here. And you're using the same radius, so you should not be touching that little, what is it called? The adjusting knob, okay? So don't touch that. Keep it the same. And then you're going to do the same thing here on this point, okay? So pointy in there, and you're going to draw this part right here, all right? Now, after you get that X marks the spot aspect, what you're going to do is you're going to draw, finally, our angle bisectors. So notice how this line right here, you can draw from R all the way through that X marks the spot, and you're going to do the same thing here, okay? Now, where they meet up, where they intersect, that's your end center. That's your point C. And then, lastly, you finally put the pointy part right there. Oops, sorry. Right at your end center. And then you're going to be able to draw that circle that you need. Okay? That inscribed circle. So again, this is the order, guys. You're going to pointy part on your angle, P, okay? Draw your major arc right there. And then what's going to happen is you're going to get this point right here. You're going to put the pointy end of your compass there, and you're going to draw a little minor arc here. Then pointy part right here. Thank you, little pen, for being so fun. There we go. Again, pointy part here. Draw your other arc. You should get some kind of X going on right there. And you're going to do the same for R. Major arc. Okay. Got your points, pointy end. You're going to measure out, again, another little minor arc. And you got your point here, pointy end, another minor arc. And then you're going to be able to draw from this point, from P, through the X marks the spot, okay, through those minor arcs. And then same thing with R, all right? And then where they intersect is going to be your end center, and then you're going to be able to draw a circle with the point in the pointy part of your compass right there at the end circle, and that's going to help you draw your inscribed circle, okay? So try to do that, listen to the instructions, and try your best to do this on your own, okay? All right, moving on, using properties of angle bisectors. So basically with angle bisectors, again, this angle is the same as this angle over here is the same as this angle, and this angle is the same as this angle. Okay, those are angle bisectors. So these lines created are angle bisectors. Now, when you have three angle bisectors going on here, and again, here's your in center right here, if you were to draw a circle inside, basically it's just saying that px, okay, or this guy right here, is going to be the same length as py, this guy right here, and pz, this guy right here. That's the main idea, okay, by the in-center theorem. If you have those intersecting angle bisectors, basically that point, that in-center, is going to create those three measurements, those three side lengths, or I'm not side lengths, those three lengths, line segments, and they're all going to be congruent to each other. That's basically all it's saying. So in example 3, if we were to use this, the distance from V to KL, again, they tell you that, let's see, KL is right here. Oops, thank you, pen, for doing that again. If only technology was 100% awesome like that, you know? All right, there we go. Basically, the distance from VW, okay, is going to be the same as the distance from KL to V. So basically, the in-center of this triangle is right here. And by the in-center theorem, we know that V is equidistant to the sides of the triangle itself. So if we go from the distance from V to JK, which is 7.3, the distance from V to KL is also going to be 7.3. So again, if you were to ask, what about JL? Well, fun fact, JL also has to be congruent or the same distance because of the in-center theorem. There we go. All right, so take your time. Again, we're trying to figure out the measurements that they're requesting. Now, for angle VKL, this is part B, okay? For angle VKL, again, let me clean this up for you guys so you can see the fresh work here. They go ahead and give us a couple angles. Now, VKL is this guy right here, this angle right there, right? Now, they do give us a couple angles. They do give us this larger angle here, and they do give us this angle right here. Now, JV is the bisector, and again, I'm filling the blanks here, so bear with me. JV is the bisector of angle, so let's see, JV is the bisector of angle, looks like KJL, okay? Cuts this angle in half. There's the triangle sum theorem, so we're subtracting blank from each side. Let me see what they're talking about here. KV is a bisector of, okay. So let's see, if this guy is 19 degrees, that means there's another 19 degrees here because he's an angle bisector, right? So that basically we have 38 degrees for the whole angle. Now, if that's for the whole angle, basically, again, this whole guy should be 38 degrees. Now, we're not sure, so we can double check. We know this whole angle has to be 38 degrees. So we have this triangle here. We have 109 degrees for sure. We have 38 degrees for sure. We know the triangle sum theorem is 180 degrees for a triangle. Okay, we learned that before earlier. So we have, again, 180 minus the 109, you get 71 degrees, minus the 38, and we should get 33 degrees. So that means it's not 38 degrees here, it's 33 degrees. So if that's 33 degrees, okay, we know that this angle should be the same as this angle because that's an angle bisector. So what's half of 33? All right, and you should get, I believe, I'm trying to do the math in my head, it's not pretty, 16.5. All right, so subtract, I don't know what they're trying to say here. Again, I don't like filling the blanks. But basically the measure for JKL is 19 degrees, right? And we multiplied that, we got the 38, okay? So that's what happened right here. Okay, we knew that was half of the whole thing, so 2 times 19 is 38 degrees. And then we know, well, we have the 38 degrees plus the 106 degrees plus the other angle, the bigger angle right here, okay, which should equal 180. And again, that's the triangle sum theorem. So we have our answer, which is, well, not our answer, but we have what's left over. Oops, not 71, 33 I said. Silly me. All right, so you got your 33 degrees. We know that that's an angle bisector in the middle, which should cut the 33 degrees in half. So you should be left with 16.5 degrees. Not a pretty answer, but it works nonetheless. So again, it's very logic based. Use the theorems and you should be just fine. All right, so your turn number 4. Find the distance from x to PQ. So again, x to PQ is right here. Thank you, touchscreen, for, again, making my day wonderful. I spend probably 20 seconds every video or 30 seconds every video just trying to fix that. So again, the distance is labeled right there in the little mark that I made. The answer, I will give you a hint, the answer is literally in that picture somewhere. Okay, so you just have to get that idea of, you have your in-center and then you have the distances from those sides from your in-center. Now, what's the measurement for angle PQX? So let's label that PQX. So it's asking about this angle right here. They do give you this angle here, which is an angle bisector, right? So technically, how many 12 degrees are there in that corner? And then you have this angle given to you, 52 degrees. And then, so basically, you're just going to have, well, your measurement for, again, QPR plus your angle of QRP. And don't forget, angle QRP has 2 angle bisectors, and they did give you one of them, okay? Plus angle PQR, and they all have to add up to 180 degrees, all right? And don't forget, whatever you get for angle PQR, they're only asking for half of it, okay? So you're going to multiply or divide by 2, and you're going to get your answer, okay? So don't forget that, because they're asking for this little part, not the whole thing. All right, guys. If you have any questions, let me know. Any issues with constructions, let me know. Again, this video is only to supplement the idea of what you're doing. You should be hitting me up whenever you're confused. All right, so let me know what's going on, and have a great day.